thanks for the invitation. I feel lucky that I was still here as well. So I just wanted to give a brief overview of the kinds of things that we've been working on at NCAR with regards to the climate of the last millennium. And you notice I have a massive list of co-authors here. So I gave a lot of this material at the CESM workshop in June, so apologies if this is repeated. But I just wanted to highlight how many people have been involved both with the running and the development of the code and conducting the experiments and also doing the science with all of our last millennium experiments here at NCAR. So many kudos to everybody involved here and elsewhere. So, okay. So just, if you haven't read this paper yet, this is our BAMS paper that came out in 2016. Betty Otto-Bliesner, who's the head of my group, was the lead on that. And this just summarizes the experiments that are part of the last millennium ensemble. So this is a massive set now of experiments. There's over 30 simulations that have been conducted with CESM1. And they comprise the climate of the last 1,000 years. So it goes from 850 to 2005, and we actually have some extensions now all the way out to 2100 with the RCP 8.5 scenario. So it's a pretty massive investment on NCAR's part. There's been many millions of core hours involved in this. And I just wanted to put this table up because these are what I'm calling the core experiments. So this is a table from the BAMS paper where we presented the experiments. And just to highlight that these numbers are no longer accurate, we've actually done more simulations since then. And the other key thing about the LME is that we have what we're calling full forcing experiments, where we include all natural and anthropogenic forcing, so greenhouse gases, aerosols, orbital forcing, solar, volcanoes, all that. And then we've also done sub-ensembles where we've only included individual forcings. So I guess for the ozone and aerosol only, that's the one thing to highlight. That only goes from 1850 onwards because we didn't have forcing data sets prior to that. But there's a lot of experiments. They're all publicly available. I think maybe some people will be using that and presenting those results during this meeting. I'm not sure. But LME is great. There's also a lot of people outside of NCAR working on these experiments. So this is the LME project webpage that you can go to if you're interested in the kinds of things that the university community is doing with the LME. And we ask that if you are working on LME output, then you just send us an email, either me or somebody, Betty, in the group, and we'll put you on the webpage. So there's a project descriptions there. And I mentioned that that table was just the core LME experiments, so we're also doing additional sensitivity runs to extend the capacity of the LME to simulate the climate of the last millennium. So one thing we're doing is looking at aspects of forcing uncertainties, particularly with regards to volcanic aerosols. So we varied the season of the eruptions of Tambora and Somalis in Indonesia. And that was published this year. We also have a simulation where we increased the magnitude of solar forcing. That's not published yet, but it is completed. I'll be focusing on the later part of the talk on the isotope-enabled last millennium runs. So that was not available when we started the first set of LME simulations, but now we're actually doing a suite of CESM 1.2 experiments to complement the LME, and we have oxygen isotopes in the atmosphere, ocean, land, and sea ice. And we have another simulation with radiocarbon isotopes as well. And I'm not sure if I'll have time to get to this, but we have some simulations where we've actually simulated the eruption of Mount Tambora in the 21st century. So that just came out in Nature Climate Change, and John Fasillo was the lead on that study. So there's a lot of stuff going on. And we're always doing more experiments and looking for new collaborators. So please come talk to us if you're interested. Okay, so I like to highlight the things that are really unique about having an ensemble like this. So one of the key capacities of the LME is the ability to identify force changes of last millennium climate. And hopefully this is going to be relevant to your work with the LMR. So because we have these simulations that have individual forcings, as well as the full forcing simulations, you can start to do attributions. Not so much, we haven't done like so many formal detection attribution studies, but the experimental design is really convenient for this. So just as an example, you can identify the force trends in northern hemisphere mean temperature. So I have time series from 850 to 2005 of the said northern hemisphere mean temperature. And the dots up there on the top plot are big volcanic eruptions. And so what you can see is that when you have a massive eruption, you cool the northern hemisphere climate. So, not the most groundbreaking result, but it is fairly striking. And what you can also see that's kind of interesting here is that in the volcanic suite of experiments, in the volcanic, which is the purple, and in the full forcing simulations, which is the gray envelope there, you actually see this millennial scale cooling trend, which is the cumulative impact of all of the volcanic eruptions. And so so you can start to really parse out all the force changes that you're seeing here. And that cooling trend is not apparent in, for example, the greenhouse gas or the ozone and aerosol simulations. And then down here, just as a contrast, I pulled it out because it got messy when everything was on the same plot. But these are the single forcing simulations which don't have any anthropogenic or volcanic impacts in them. And you see slightly different trends. And we haven't done a great deal with these northern hemisphere temperature signatures, but I just thought they were an interesting example as something that the LME is really good at. You can also look at force changes to modes of variability. So this turns out to be quite hard to do over the last millennium because a lot of the forcings are very small compared to other paleoclimate epochs like the Metallocene or the last glacial maximum or so forth. But you can see some force changes to climate modes, particularly the AMO. So this is a figure from our BAMS paper, just showing the spectra of ENSO and the AMO in different sets of LME simulations. So the black envelope here is the full force, like everything with the full forcing simulations. Then the red is all of the simulations in the LME which don't have volcanoes, and the blue is all the ones which do. And you see that there's not a lot of change in the ENSO spectral behavior, but there is a marked increase in the AMO variance at low frequencies. So you can actually directly see, just from looking at this output, that volcanoes are exciting AMO variability. So this is another key feature of setting up experiments like this. You can see force changes to the tropical Pacific mean state as well. So just another example. This is the difference in tropical SST between the 20th century epochs and the pre-industrial epochs in different sets of LME experiments. So in this set of simulations, 20th century forcing tends to lead to a slight warming over the Western Pacific warm pool and an increase in the equatorial trade. So that's the full forcing panel on the top there. And when you look at the single forcing experiments, you see that all of these things are actually interacting with each other to give you that net forced impact. So greenhouse gases tend to warm the eastern equatorial Pacific preferentially and weaken the trade winds, whereas aerosol forcing does the opposite. And I have land use and land cover in here because they do interesting things to ENSO that I'll show you in a minute, but it doesn't do as much to the mean climate. So you can kind of think of the full forcing cases as being a superposition of these different forcings, although I don't know whether it's exactly linear. It's probably not because it's the climate system. So there are force changes to ENSO. So I showed you that spectrum, that we don't see like a whole lot of change to the overall spectral power, but you can piece out changes to the ENSO dynamical response here. So this is a Hofmüller diagram of equatorial Pacific SST anomalies across the peak of an El Nino. So that top plot is what an El Nino looks like in the control run. So this is just what CESM wants to do when it has an El Nino. It's warm in the eastern equatorial Pacific, which is good, because that's what we defined El Nino to be, right? So 0 is El Nino peak, and then we go from 2 years prior to 2 years after that. And then the difference, again, between the 20th century and the pre-industrial run and the full forcing experiment is here. So El Nino doesn't change a whole lot due to 20th century forcing. So maybe it's just not interesting. Well, if you, again, look at these single forcing experiments, you can see that there are force changes. They're small, but they're there. And so if you look at the greenhouse gas force, single forcing ensemble, for example, the 20th century tends to have El Ninos which terminate preferentially compared to the pre-industrial run. So there's this cold anomaly after the peak of the El Nino event. So you're killing the El Ninos and leading to a La Nina more efficiently due to greenhouse forcing. But that's compensated once again by the role of aerosols. So then you have this warm event, or warm anomaly after the peak of the El Nino. So there's something going on in here that is more complex than you might expect just from looking at the full forcing simulations. And it mentioned land use. So this one was weird, and I still am working on the details of this, but if you have no forcing other than changing land use and land cover over the last millennium, you tend to make El Niños stronger. So we have this massive warm SST anomaly in the eastern equatorial Pacific during El Nino peak. So it's making especially extreme eastern Pacific El Niños stronger. And again, it doesn't show up that well in the full forcing experiments, but it's something that we might want to pay attention to just to understand the dynamics of this. Okay, so I'm not going to get into that in too much detail, but I wanted to move on to the next key LME capacity, which is the ability to separate these force changes from modes of coupled atmosphere-ocean variability like ENSO and their remote impacts. So I notice we have a lot of talks about drought later on in the LMR agenda, which is exciting, but because I like to think about megadrought as well. So these are these really strong decadal drought events that we see in the paleo record, things like whole lakes drying out and tree stumps being left behind. And we see these in the model as well. And we think that they're related to ENSO. There's some question as to whether they're related to external forcing. And this is another thing that we can start to get at with big ensembles like the LME. So we can treat this as a kind of big data problem, Silicon Valley speak. But because we have 30,000 years plus of simulations, we can look at the statistical associations between these very rare megadrought events and ENSO variability and things like volcanic forcing. Okay, so this is a time series of a drought index called PDSI over a particular area. This is just a cartoon illustration. So this is the North American Southwest. And you see that you have some wet periods, so positive anomalies, and some dry periods, which are negative anomalies. And you can't do this just with the proxy record or with a single simulation, but when you have enough simulations, then you can actually break this into pieces. So in the plots I'll show you in a minute, it took a 200-year moving window, moved that across the time series at every grid point in the model. And at every grid point in every 200-year chunk, you have a value for ENSO. You have a value for what these droughts are doing as well. So you have a certain number of them, right? Maybe you have 0, maybe you have, I don't know, 1. And it lasts for a certain amount of time. And there's a certain risk associated with that. So that would be the percentage of this 200 years that conditions are appropriate for a megadrought. And just as an illustration, this is where the droughts actually are, these yellow bars here. So they're rare, but we can study them. And if you look at how, for example, ENSO is related to drought risk, then you can make maps like this. So up top is the risk of a megadrought in the entire LME, so again, these 30,000 years plus of simulations. And this is the risk when ENSO tends to be relatively weak. So I mentioned you have these 200-year chunks. So for every grid point you have, what is that, 5 times the number of simulations. So a lot of points, and then you pick those epochs when ENSO tends to be relatively weak. So in this case, it's below the 40th percentile. So arid regions have a higher risk of drought. Again, not the most earth-shattering result. So places like Australia, the Sahel, the Middle East, North American Southwest to some extent have a higher risk of drought. Okay, the Amazon, Indonesia, they have lower risk of drought in general. And then what's interesting to me is that you can make this map down here. So you can say, okay, this is the risk that we had to begin with. What's the change between periods when ENSO is strong versus weak? And what you see is that there can be a significant change. I think the stippling is a little bit hard to see, but you can do significance testing on this as well. And some areas pop out, right? So like you have Mexico, you have the Amazon Basin, you have Australia. These are all places that have significant changes in drought risk when, as a function of the ENSO amplitude in the model. And then the Southwest US has a slight reduction in drought risk as well. So I just wanted to point that out briefly. And this is interesting. This happens in other places as well. So this happens in both the US Southwest and in Australia. But essentially what's happening is that when you have a stronger amount of ENSO variability, you're alternating between El Nino and La Nina more efficiently. So you have stronger SST anomalies, basically. And that tends to be associated preferentially with the starting or the ending year of a megadrought. So this is the probability, the PDF of the Central Equatorial Pacific SST, so it's Nino 3.4 index. And what you see here is that when you have the ending year of a megadrought, so you just take that end year of every drought within your 200-year chunks, whatever, and that PDF is shifted preferentially towards El Nino events. so these are associated with terminating these drought events. And conversely, when you have the starting year of a megadrought, you have a La Nina. So, and this is consistent with the teleconnection to ENSO in that location. So if you make this plot for Australia, it looks the same, but the red and blue curves are swapped because the teleconnection is the opposite, goes the opposite direction. So this is a thing you can do when you have a big ensemble, is you can actually start to measure these associations that we expected would be present. Okay, so just schematically, this is kind of my thought process for using the LME to look at these kinds of things. So you have your thing you're interested in this case, megadrought, and it's going to be associated with regional variations in hydroclimate, right? So you have your land processes and all of that. And those are related to modes of climate variability like ENSO. They're also related to volcanic forcing, which I'm not really going to discuss in this case, but all of those interact. And to really understand that, you need either dedicated sensitivity experiments or to do statistical associations with large ensembles like the LME. Okay, so I just wanted to, I have a lot of things I wanted to tell you about, so I'm going to skip over some of it. But I just wanted to point out one other thing, which is that if you're trying to look at external forcing, particularly volcanoes, so this is the biggest forcing over the last millennium, right? And this is another reason why we need these big ensembles, is that there's a massive amount of internal variability in the climate system. So this is the response of the tropical Pacific to the eruption of Tambora in 1815. So this is the same model, the same eruption, same everything except for the initial conditions. And you see that about half the time you get an El Nino event, and the other half, the tropical Pacific does something else. And there's various reasons for this, but basically, if you're talking about the proxy record, or the real climate system, we only have one realization, right? So it could be this, it could be this, it could be any of these. And so this is where looking at these big ensembles is really valuable. Okay, so I'll skip over the volcanic stuff a bit. But one goal that we have at NCAR, and I would hope as a community, is to improve our ability to compare models with proxy output. So how well do we understand the climate system? How well do we understand what the records that we have of the last millennium are telling us? And you know, we're all here to understand the last millennium. So one thing that we've been thinking about a great deal at NCAR is the uncertainties in the forcings themselves. So we have all this internal variability in the climate system. We also don't really understand the forcings all that well. And I like this figure because it's a really good illustration of this is our best state of knowledge of the volcanic aerosol forcing over the last millennium. Right, so which one is which? Okay, so this is a new reconstruction of volcanic aerosol forcing over the last 2,000 years. And this just came out a couple of years ago. And it's updated, so there, you know, you basically take your ice core records from Greenland and Antarctica and then make an estimate of what we think the aerosol loading in the atmosphere was and use that to force climate models. Right, so this is the best estimate as of 2014, and the green bars are the difference between that and our best estimate from 2008, which, and this GAO reconstruction is what we used for the LME, just as a sidebar. So these percentages on here are quite disturbing, right? So this changes the strength of the Somalis eruption by tens of percent, right? So there's a big uncertainties in the system. And so, you know, you can imagine that if your model doesn't compare well with the proxy record, maybe it's not because we don't understand the proxies or the models are wrong, it's because we're telling the model something that didn't actually happen. And so we're trying to understand all of the various uncertainties that are involved in this. So one thing that's uncertain, in addition to the magnitude of the forcing, is where the aerosols go, right? So you take your ice core record and you make a latitudinally dependent forcing data set. But the structure of that forcing in latitude matters a lot, right? So this is just what the CESM and the LME does in response to volcanoes that happen to have loading in different hemispheres. So if you have a tropical eruption, you tend to get an El Nino the year after the eruption. So that's that El Nino on the left-hand side, that plot over there. No, right-hand side, sorry. Yeah, okay. And then the northern hemisphere has an El Nino initiation, which happens a bit earlier than the tropical eruptions. And this is actually because of the behavior of the ITCZ depends on the hemisphere of the eruption. And if you have a southern hemisphere volcanic eruption, which is relatively rare because there's not that many volcanoes in the southern hemisphere compared to the north, then you don't tend to get that kind of El Nino initiation. So the hemisphere matters quite a bit. And also the season matters. So I'm just going to put a crazy hypothesis out there, which is that most volcanoes probably all didn't happen in April. Okay? But that's not what CESM thinks. So this figure was kind of amazing to us when we started looking at the behavior of CESM. So this is the clear sky albedo in response to volcanic eruptions. And you might notice that they all look pretty much the same. And this is because we don't know exactly when all these eruptions happened, because we didn't have historical records a lot of the time. All we have is these ice cores. And so you can tell what year it happened, but you don't know the month always. And so you have to pick something. And so what Gao et al., this reconstruction that we used through the LME did, is they just picked April. And you end up with something like 2/3 of the volcanoes over the last millennium happening in April, which is maybe that could happen, but it's unlikely, I think, and it matters. So one thing that has been in the literature for a little while is the fact that models don't see the same hydroclimate patterns in an eruption year as the proxy record does. So this is the PDSI Stroud Index anomaly for boreal summer of an eruption year. So in Southeast Asia, you see a wetting anomaly, and in the Southwest US, you see a drying, and you don't in the LME. But when we varied the season of two big eruptions that happen to be tropical, in this case, you see that you get really different soil moisture patterns in the few months following the eruption. And so in this case, this is April versus July. So these are model results here. So this is an issue. And the other thing is that if you're compositing on a certain season, like you are in the Trian record, because that's the growing season and you have to, but maybe your eruption didn't happen until October, and you don't know that, so maybe you're compositing some summer values from an eruption that has not happened yet. So this is another area where you have to be really careful about model proxy comparisons. And I don't have a solution for this other than comprehensively going back and looking at eruption season for the entire last millennium. But yeah, it's hard, so it's a thing we should think about more. And then I also wanted to get to isotopes a little bit. So I wanted to also point out that we need to understand the proxy signals themselves better. So this is a figure from Kim's paper a few years ago showing the change in standard deviation of coral isotope records in the interannual band. So here we have stronger ENSO versus weaker ENSO over the entire Holocene. And what you see is that you have an intensification of variance over the late 20th century, which is stronger than anything over the Holocene. And I think there's a lot more records now, and Kim will probably fill you in on all the details of this. But I just wanted to point out there's this increase in variance, but we don't actually understand all of the mechanisms yet. So this is the formula for the deltoid of coral, which is what this variance actually is. And there's a component of temperature to it. So this increase in variance could be due to an actual increase in SST variability, or it could be due to a change in the hydrological impacts of El Nino events at the locations of these coral records. And this is a thing that we can constrain observationally, but it's very hard to do because it requires multiple geochemical measurements. And it's also important for understanding what the climate models are doing. So just as an example, this is the Nino 3.4 variance from the LME. And we also see this very slight increase in late 20th century variability. So maybe CESM's just right, and we can all go home, but maybe not. So the problem from a modeling perspective is really different if you are trying to capture an increase in SST variability versus you're trying to capture an increase in hydrological impacts. Like there's different things you would have to fix in the model. So we want to know this. And the only way to really do this correctly is to do isotope-enabled simulations. So just another plug for some new simulations we're doing at NCAR. So they're actually running right now. But we're trying to do a mini LME with isotopes, the water isotopes. we have our full forcing simulations. We're going to do 3. One is finished and the other 2 are running. And then we're going to try to do as many of these as we can get through before our allocation expires. So we're going to try and do 3 greenhouse gas, 3 volcanic aerosols, and then subsets of the other forcings. And we have a description paper in the works for the model, so not for the LME runs necessarily, but for the ICESM model, which has been a massive effort on the part of both NCAR and David Noon's group and other people. So it's been a lot of code development, and this is really exciting. Okay, so the ILME full forcing experiment looks pretty good. So this is also super exciting. So we're able to correctly simulate the both the precipitation amount and the delta 18 of precipitation, so the isotope ratios and precip, over, this is the late 20th century, so 1950 to 1999. So the colors are the model output, and the circles are the GNIP stations. So these are actual in situ measurements. So we're doing quite well. So we think this is really exciting. I mean, it's a model, so the performance is never perfect, but it's looking really good. Just to show you what types of things you can do with this. So if you look at the impacts of ENSO on both precipitation and the isotopic ratio of precipitation, you can see that you're sensing different things, right? So here the contours are the regression of Niño 3.4 on precipitation. So it rains more here over the central Pacific, and it rains less over the western Pacific when you have an El Nino event. But then there's different signatures in the isotopes of precipitation. So for example, over Australia, you have this really strong isotopic signature. So you're changing the isotopic composition of precip more than you're changing the amount. So you can imagine if you have proxies that are sensing different things, then they might be telling you different aspects of ENSO dynamics. So I don't understand all the details of this figure yet. I just thought it was cool. And then you can also look at the seawater delta 18 impacts of ENSO. So this is what would be relevant, among other things, for understanding that coral variance plot I showed you. So similar to salinity, you get fresh anomalies in the central Pacific during an El Nino event. So the warm pool expands, you get heavier rainfall, all that sort of thing. So you really want to understand how these patterns are changing in response to external forcing to understand exactly what the coral records are telling you. So then, just as an example of one thing you can do, you can look at volcanic eruptions. So again, the formula for the coral delta 18 is there. So you have your temperature components and you have your seawater isotope components. So this is what you would see in the model. Well, it's what you would see if you had a coral at every grid point, which would be amazing. But you are sensing in isotope space this really strong El Nino-like response to both tropical and northern hemisphere eruptions. And this is primarily due to temperature, as you can see, because you don't see this very strong seawater delta 18 response over the eastern equatorial Pacific. So it's mostly a temperature signal. But what's cool is that there seems to be a hemispheric dependence of the hydrological response to volcanoes, right? So you get a response over the warm pool here. So there's this enriched anomaly in isotope space. But you see a different response kind of off the equator near where the SPCZ is most active in response to northern hemisphere eruptions. So isotopes are telling you something fundamental about changes to the hydrological responses to both external forcing and modes of climate variability. Let's get the monsoon. And then I just wanted, in my last couple minutes, I don't want to take up too much of your time, but to get back to this 20th century forcing issue. So we had our coral plot, and we say, okay, maybe there are changes to the hydrological impacts of ENSO. Is that something that we see in this model? Well, sort of. So this is a Hofmuller diagram again of equatorial precip. So this is the structure of precipitation changes that you see during an El Nino event, with the increase of precip in the east and the decrease in the west. And this dipolar pattern is compensated in the difference between the 20th century and the pre-industrial here. So that's over on the right. So you tend to suppress the changes in precipitation that an El Nino causes in the 20th century compared to the pre-industrial in the CESM, even though the variance is increasing a little bit. So this is different than the response that we expect under climate change, but it's kind of interesting. But despite that, we tend to see an amplification of the isotopic response during an El Nino event in the 20th century in some places. So this is the composite of seawater, Delta 18O, in the pre-industrial during an El Nino event. And then this is the difference between the 20th century and the pre-industrial. And so we see a decrease here in the Western Pacific, but there's this increase over here. And just for reference, we have coral records from a lot of these islands. And so there's an increase because these anomalies are actually shifting to the east in response to 20th century climate forcing. So there's some places where you might expect to see this increase in seawater delta 18 variability. And particularly, again, off the equator in the South Pacific is a place where you tend to see an amplification of hydrological impacts of El Nino. So that's interesting, and this kind of tells you the sorts of things that maybe you might expect dynamically. And so these are features that you can start to look for in the coral records. And we don't see a big effect in the central equatorial Pacific where Kim's records are. But so maybe that suggests that we should be interpreting that increase in variance as temperature. But there's all these caveats. It's only one model and so forth. So this is very, very preliminary. But it just points to the types of things that you can be thinking about. And then just as a broader picture, you can start to understand the percentage of variance that's due to temperature versus seawater, delta 18 variability. I don't want to get into this too much, but this is essentially a method of decomposing the variance due to either temperature or hydrological impacts in a coral record. And again, the pre-industrial and the difference in the 20th century versus pre-industrial. And you see a weakening here and a strengthening here. So maybe if you've got coral records in a certain location, you might expect the amount of variance that's being caused by these hydrological impacts to be increasing or decreasing. So again, these are kind of ways that isotope-enabled simulations are incredibly valuable both for modelers and for proxy people and can bring us all together and are great. All right, so in conclusion, so the LME is a fantastic community resource. If you haven't already downloaded or gone to this website, feel free. The advantages of large ensembles are many. So you need them to robustly separate forced climate signals from internal variability. So it's good for temperature, it's good for understanding ENSO dynamics and mean state changes, probably a bunch of other things I'm not thinking about right now. You can also think about the remote impacts of modes of climate variability and start to disentangle changes to teleconnections versus changes to forcing versus kind of stochastic atmospheric variability. And then I think that it's really important to think about these next 2 points here, which is how the hell do we understand when models and proxies don't agree? Is it the models that are wrong? Is it that we don't understand what the proxies are telling us? Or is it that the forcings are just wrong? So it's like a garbage in, garbage out scenario. So we really need to try and understand these forcing uncertainties, and the volcanic examples that I gave you are one area, but again, there's probably a lot more. But having isotope-enabled models really helps because most of the proxies actually are measuring isotopes. And then I didn't get into this too much, but these last millennium analyses can also be an important source of context for assessing the risks of things like future volcanic eruptions or future megadroughts, so that sort of thing. Okay, so hopefully that wasn't too much of an information dump, but yeah, thanks for listening and inviting me.